Hello, my friends. In this video tutorial, we are going to solve some math problems. This is actually probability problems related to die game or dice game. So let's get started. Please like, leave a comment, and subscribe. It will push YouTube algorithms and promote channel. It will also make me happy to create new lessons. And please don't forget to push this bell button to get new videos. First of all, we have to understand that die can be represented as discrete random variable. We denote this random variable as x, for example, and our die can take 6 outcomes. Outcome number 1, we denote it as omega 1, small omega 1. This is 1 when we have 1 on up front of our die. Here we have 1. It can be 2, 3, 4, 5, and 6. And we have a concept of fair die, meaning that probability of each outcome is 1/6. We know that total probability is 1, and the probability of getting each number of dots is equal. This is 1/6, so with the same probability we can get 2, 3, 4, 5, 6, and 1. When we want to calculate expected value of the number of dots that we have here, expected value of random variable, this is also denoted as E from expectation. This is expectation. This is the sum. This is the sum over each outcome. So we have I from 1 to 6. Outcome number I times the probability I. And here, this is P1, the probability of getting 1, 2, and so on. This is P6. And this is called mathematical expectation or expected value. Let's begin with the problem. Let's write down this problem. The player tosses a die only once. Okay? The payoff is $1. For each dot on the upturned face. Assuming this is the fair die, what is fair ticket price of this game? So once again, the player tosses a die only once. Okay, so the player tosses a die only once, and the payoff is $1. So we receive $1 for each dot on the upturned face. So for example, if we have here 1, we receive $1. If we have 6, we receive $6. So this is the game. And of course, you make money playing this game. And of course, the ticket must be, we have to find the fair price of this ticket. The concept is that the fair price of the ticket for this game, when the player tosses a die only once, so we have only one toss. The fair price is equal to expected value we defined earlier. So this is the fair price, because the concept is that if we play this game infinitely, then the money we make, the payoff we receive, is equal to the price of the ticket. Okay, so this is sum from 1 to 6, I times 1 over 6. And of course, this 1 over 6 can be taken out of the summation, and we have the sum from 1 to 6 times 1 over 6. If we rewrite it, this is 1 over 6 times 1 plus 2 plus 3 plus 4 plus 5 and plus 6. How to calculate this? Obviously, we have to perform addition of 1 and 6. It will be 7. 2 plus 5 is also 7. 3 plus 4 is also 7. So we have 3 pairs of 7s. It will be 1 over 6 times, we can write it as 1 plus 6, which is 7, times 3. And 3 is 6 divided by 2. And this will be 1 over 6 times 7 times 3, which is 21. And answer is 21 over 6, or 7 over 2, which is 3.5. So 3.5 is expected number of dots if we play infinitely. That's why the fair price for the ticket answer of this problem, fair price of the ticket is $3.5. Okay, let's solve another problem and make this problem harder. And the next problem, evaluate expectation when we have evaluate expectation or fair ticket price for n-sided die. So assume that our die has not 6 sides but n sides. So we evaluate expectation or fair ticket price for n-sided die. In this case, let's begin our solution. In this case, our random variable takes a different number of values, 1, 2, 3, and so on, and n, and probability p1, p2, p3, and so on, pn, because we have a fair die, and the probability pi is 1 over n, and outcome omega I is I. So in other words, we have I dots on upturned face of a die with probability pi, which is 1 over n. Our problem is just calculate expected value of dots on upturned face, which is mathematical expectation. Once again, this is the summation from 1 to n, omega I times the probability of this outcome, which is I times 1 over n. And once again, as in the previous problem, this 1 over n can be taken out of the summation because it doesn't have I index, and our problem boils down to this I, which is actually 1 over n times 1 plus 2 plus 3 and so on plus n. And as in previous problem, it will be equal to n plus 1 or n plus 1 times n divided by 2. So when we have summation 1 plus 2 plus 3 plus and so on n, like in previous problem, we can write it as n plus 1 times n divided by 2. This is easy to prove. If you don't understand, watch our previous problem. And this is, of course, 1 over n times this. And we have here the cancellation of n and this n. And answer will be n plus 1 divided by 2. So n plus 1 divided by 2 is expected number of dots on upturned face of our n-sided die. And of course, if n is 6, in this case, n plus 1 divided by 2 is 7 over 2, which is 3.5, as in our previous problem. So it was the solution. And of course, in this case, answer is n plus 1 divided by $2. This is the fair price of the game. When you buy a ticket and play this game, the fair price for this ticket must be n plus 1 divided by 2. Okay, let's solve next problem. Only solving the problem we can understand the theory. That's why theory is important, but solving the problem is much more important. Next problem is what is expected value or expectation of the sum of two rows. What does it mean? In previous problems, we assume that we have one roll and we roll our die one time. Here, we roll once, then we roll the second time, so we have two rolls. And what is expected value or expectation of the number of the sum of two rolls, or the sum of the number of two dots on upfront faces? For example, we rolled dice first time and we have here 3 dots, and second time this was the first time. The second time, assume we have 2. So in this case, we have the sum of two rolls. 3 plus 2 is 5. And what is expected value of the sum of these two rolls when we, the concept is when we play this game infinitely? So let's solve it. In this case, we have next situation. We have I, let's write here I and G, and we have the first roll can give us 1, 2, 3, 4, 5, and 6. And second roll also can give us 1, 2, 3, 4, 5, and 6. And let's assume the sum of these two numbers, number of dots for each die. And we have here 1 plus 1, 2, 2 plus 1, 3, 4, 5, 6, 7. It's important to note that this 2, 3, 4, 5, and 7 is like 1, 2, 3, 4, 5, and 6, but it is shifted by 1, okay? Next, our numbers 1, 2, 3, 4, 5, and 6 will be shifted by 2, and it will be 1 plus 2 is 3, 2 plus 2 is 4, 3 plus 2 is 5, and so on. And let's fill our table. It will be 1 plus 3, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, and 7, 8, 9, 10, 11, and 12. And for example, this 12 is received as a sum of this 6 and this 6. So expected value, we have to calculate expected value. Expected value is equal to the sum of I and G from 1 to 6. And we have here the sum of the number of two rows, I plus G, times, because we have here in this table, we have 6 times 6 outcomes, 36 outcomes. And because our die is fair, that's why the probability of each this outcome is 1 over 36. And we have 1 over 36. And we have to just calculate this sum. Let's do it. And here we can, of course, this number 1 over 36 can be taken out of the summation, and we have 1 over 36 times, let's rewrite our sum. And what is the sum of I and G when I and G from 1 to 6? This is just the sum of elements of this table, of this matrix. We can calculate it using some calculator, for example, but let's be smarter. Let's use some mathematical way of the calculation, because we can have here not 6, but n, for example. That's why we have to learn how to calculate this sort of problems without calculator. And of course, it's important to note that this first, for example, row is 1. What is the difference of these two rows? 1, 2, 3, 4, 5, and 6, and 2, 3, 4, 5, and 6. Easy. It's easy to see that this row is the shifted version of this row by 1. So we are going to calculate the sum of these 6 rows. This is 1 plus 2 plus so on plus 6. This is 6 times, okay? And plus, because we have shift here, we have here shifted by 1, by 2, by 3, and so on. And we have 6 times because we have 6 rows, and each first shift is 1, the second shift is 2, and so on, plus 6. And using previous problems, this is equal to 7 over 2, or 3.5. So we have, no, this is equal to 6 plus 1 times 3, which is 21, okay? And we have 21 times 6 plus 6 times, this is also will be 21. So we have 21 times 6, 2 times. 2 times. And of course, we forgot to divide all of this by 1 over 36. Okay. Divide all of this by 1 over 36. Next, 1 over 36 is 6 times 6. And our 21 is 7 times 3. And let's rewrite 6 times 2. Here, 6 and 6 are cancelled out. And this 6 can be cancelled by this 3 and 2. And answer is 7. So 7 is expected number of the sum of the number of two dots on upfront faces when we roll our die 2 times. Next problem is quite easy problem, but anyway, let's solve it. And this is our previous problem. What is the probability? What is the probability? What is the probability of getting 7 with 2 rolls? With 2 rolls. So in our previous problem, we roll our die 2 times, and let's solve it. Easily, we can see from this table where we have, as we noted, we have 36 outcomes. What is the probability? What's the probability of getting 7 in these 2 rolls? Let's look at the table of 2 rolls of our die. In this 36 outcomes, we have 7 on diagonal of our matrix of our table. So this is the first outcome, second, third, 4, 5, and 6. So we have 6 sevenths, and another numbers are not equal to 7. So the probability, obviously, is equal to 6, the number of outcomes when we have 7. 7 is the sum of these 2 rolls, divided by the total number of outcomes, and answer will be 1 over 6. So the probability of getting 7 in 2 rolls is 1 over 6.